Welcome back. In this lesson, we're going to be talking about humidity and some vocabulary associated with that. In the last lesson, we closed by talking about the dew point. And we said that if we had a superheated vapor mixture and we cool it until the first drop of liquid condenses, then that temperature where that first drop of liquid forms is called the dew point temperature. And using the simplified form of Raoult's law, we know that the partial pressure of that condensable liquid is equal to the vapor pressure of that condensable liquid at that temperature, the dew point temperature. We also briefly described degrees of superheat, and we said that for a pure substance, if we did this experiment, the dew point would happen at the boiling point, and that those two would be interchangeable in the case of a pure substance. Now, we want to add some new terminology. And most of the time when you've heard some of these words, which I'm sure you've heard about them in terms of, say, the weather and air and water systems. When we call them humidity, we usually are meaning air and water. But when we call them saturation, we're usually talking about other systems, but technically they're fairly interchangeable. So, relative humidity you've probably heard of. It's also called relative saturation. The designation, if you're talking about a general system, would be an S subscript R. For a water system, air and water, would be H with the subscript R. But what that is it's the partial pressure of, say, the water or the condensable substance divided by the vapor pressure times 100%. Now, if you'll recall Raoult's law, says that the partial pressure is equal to the vapor pressure at that temperature for a system that is at saturation. So we're wanting to see how close we are to reaching this magical point. So we're going to take a ratio of the vapor pressure or partial pressure over the vapor pressure and times 100%, and will give us a percent relative humidity. Sometimes, though, we'll talk about some other types of humidities or saturations. The absolute humidity is one that is fairly practical, okay? And it tells me the mass of vapor over the mass of dry gas. So this is not the total amount of gas. This is if you took that part that could condense out. So if you were talking about an air and water system, this is just the air, not the water. And so in order to get that, that's going to be the partial pressure, but because I want it in mass, I'm going to multiply by the molecular mass of substance I, that water in the case of water and air system. And then I'm going to divide by the partial pressure of the dry gas, so P minus the partial pressure of our condensable fluid, times the molecular mass of the dry gas. Those are to get me into the mass units. So absolute humidity is always a form of a mass fraction, but it's not the mass fraction that we're accustomed to. So this is a solute-free mass fraction. A molal humidity is going to be the same thing, but on a mole basis. So this one's easier to calculate. It's the partial pressure of I over the partial pressure of the dry gas. But it isn't used quite as often as the absolute humidity in the mass units. And then we finally have the percentage humidity. And that is going to really be the mole humidity divided by what it would be if you were at saturation, okay? So it's the partial pressure over the partial pressure of, let's say, water, okay, divided by the partial pressure of the dry air, right, without the stuff, times times what the partial pressure would be if you were at saturation. Well, if I'm at saturation, then Raoult's law applies. And so this is the total pressure minus the saturation. So therefore I can get that using Raoult's law, divided by saturation for the water vapor. This probably would make more sense if you were to write it as a fraction of fractions. So you can see that it's a fraction of those two fractions. So let's do this by just looking at an example. On a certain day, I chose a nice wintry day. On a brutally hot summer day, I think that looking at some cool temperatures were in order. So from a weather forecast, the weatherman says it's 46 degrees Fahrenheit, reports that the dew point temperature is 45, the atmospheric pressure is 30.28 inches of mercury, and the relative humidity is 96%. These are all things that commonly you would have, given to you on a weather forecast. My question for you is, can you use this to determine the mole fraction of water in the air? So, first we have the information given and just written in terms of our variables. So the actual temperature is 46 degrees Fahrenheit. The dew point temperature, T sub dP, is 45 degrees Fahrenheit. The total pressure is 30.28 inches of mercury, and the relative humidity, H sub R, is 96%. What we're looking for is Y of the water. Partial pressure of water is the mole fraction of water times the total pressure. It also is related to the relative humidity. So one would normally say that the relative humidity is going to be the vapor pressure over, or the partial pressure over the vapor pressure at the specific temperature times 100%. This is equal to 96%. So if I use 0.96 here, and this is Y times the total pressure, I just simply need to find the vapor pressure at 46 degrees Fahrenheit. Now I did this using a computer program, Cat2, but you don't have that available. You can do this by looking things up in the data tables. So you could do this in the steam tables. You also could do this using an Antoine equation. There are many sources that you can use to find vapor pressure. And so the vapor pressure in this particular case, what I found was 0.1532 psia, but of course we want it in inches of mercury, so that is equivalent to 0.3119 inches of mercury. So now I have the number to plug in here. I can solve for Y, and I didn't actually get the number. Let me just say. Okay, 0.009888851. Okay, ridiculous sig figs. But this is going to be the mole fraction of water per mole of dry air. And so it's going to be 0.99%, just barely less than 1% water in the air.